Hello. Let's see. First of all, we're going to start with a calorimetry problem here. So you can see what we're going to say is we've got 200 grams of ice at minus 10 degrees Celsius is placed in an insulated cup containing 300 grams of water at 10 degrees Celsius. And we're going to ask ourselves, when the system comes to equilibrium, how much of the ice has melted. Okay? So calorimetry problems in general are problems where we take different substances at different temperatures and then we mix them together. Typically we let them come to equilibrium and then we ask some question about the final state. Now this one's a little different from the ones that you've worked in class in the sense that notice what's happening here is that you've got ice here and some of it's melting but not all of it. What that means is that the final mixture is actually going to be, or the final state of the system is actually going to be a mixture of ice and water all at 0 degrees Celsius. Okay? So you've kind of seen this thing before. In the summertime, if you open up a cooler full of ice that's been sitting there for a while, then it's probably just ice and water, and that water is at 0 degrees Celsius. The ice is at 0 degrees Celsius. And if the cooler was perfectly insulated, it would stay that way forever. Okay? Of course, it's not perfectly insulated, and so the ice, in fact, will melt very slowly. But we're going to assume that it's all insulated here. So, let's see. The way we do all of these calorimetry problems is basically, they all start out the same way. Okay? We've got ice and we've got water. And so what we're going to say is the amount of heat added to the ice. I apologize in advance for my handwriting here. I hope it will get better as the semester goes on. The amount of heat added to the ice plus the amount of heat added to the water is equal to 0. Okay? That's because of the fact that it's insulated. All right, so what's going to happen here, of course, is the ice is going to be gaining heat and the water is going to be losing heat. Okay, and so the Q water is going to be negative, and that's why they can both add up to 0. Okay, now the amount of heat gained by the ice is going to have two parts here, because what happens is, first of all, the ice starts out at minus 10 degrees Celsius, and before it can melt, it's got to go up to 0 degrees Celsius. So let's start with that. Okay, so the amount of heat we add to the ice to raise its temperature up to 0 is going to equal the mass of the ice times the specific heat of ice times the change in temperature of the ice. Okay? Once it's up to 0 degrees Celsius, then it can start to melt. Okay? And so we can say plus the mass. Now this is not going to be, let me come back to this. Okay? The mass times the latent heat of fusion. This is the amount of heat that's necessary to melt ice. Okay? This m here is not going to be the total mass of all of the ice, though. It's only going to be the ice that actually melts. So let me kind of put that in there. Okay? It's the mass that actually melts times the latent heat of fusion. So this is the amount of heat that we're adding to the ice, and then plus the amount of heat that we're adding to the water. Okay? The water basically, actually it's losing heat, and the temperature is going to change while it does that. So we calculate that using the specific heat. So we say the mass of water times the specific heat of water times the change in temperature of the water. And that all equals 0. Okay? Now, let's go ahead and start putting in numbers here. Okay? The mass of the ice is 0.2 kilograms. Okay? I have to use I'm using kilograms here because the value I'm going to use for the specific heat has got kilograms in it, and the units have to cancel out. So the specific heat of ice, if we look that up in our textbook, we find it's 2090 joules per kilogram degree Celsius. Okay, times the change in temperature, which is 10 degrees Celsius, right? It's going from minus 10 up to 0. And so since the temperature is rising, that's a positive 10 degrees for delta T. Plus the mass of the ice that actually melts. And of course, that's what we're trying to calculate here. So that's M melt times the latent heat of fusion of ice, and we looked that up. That's a big number. That's 3.33 times 10 to the 5th joules per kilogram. Okay, so we're doing all of this in SI units. So there's that. Plus the mass of the water, that's 300 grams, so it's 0.3 kilograms, times the specific heat of water, which is 4,190 joules per kilogram degrees Celsius, times the change in temperature of the water. That starts out as 10 degrees Celsius and goes down to 0, and so that's actually going to be minus 10 degrees Celsius. Okay? In other words, delta T is negative because the temperature is dropping. And that, as we said, equals 0. Okay? So we start crunching some of these numbers. Let's see. We get to M melt, equals, M melt times 3.33 times 10 to the 5th joules per kilogram is equal to, and all this other crud ends up coming out to about 8,390 joules, which gives us M melt equals about 0.025 kilograms, or in other words, about 25 grams. So in other words, of our 200 grams of ice, 25 grams of that melts before we reach equilibrium. Okay? And just a reminder, what we mean by equilibrium is the whole thing comes to the same temperature. So, that's it.